Okay, great. Recently, I'm reading the paper of Wheaton, which discusses the 2+1 dimensional quantum gravity. It is a quite good paper. Okay, it's the motivation to read this paper is that we found that the jetty gravity into dimension can be solved by the random matrix theory. So I wonder how to deal with the 3D case. For in 3D, we just consider the Einstein-Hilbert action. The pure gravity at a classical level is trivial because there is no gravitational waves in 3D, which means that, as mentioned by Witten, any two solutions are locally equivalent. So one would expect a good quantum explanation for the 3D gravity. However, it seems unfortunately if you want to deal with it with the method of QFT, that is because if you just go to do the dimension analysis, then this ordinary appears this theory appears to be non-normalizable. Yes, but in reality, it is not the case. Although the non-normalizability impairs, you have to add an infinite number of terms. You found that these terms can be summed up to one thing, cosmological constant. Or you think just add just a cosmological constant. So and you can absorb this factor into G, into the metric. So any divergence can be dealt with through field right definition and the renormalization of the cosmological constant. So you don't need an infinite number of terms, but we can make the things better. We can write this theory as a gauge field theory. You can clearly see that no field right definition needed. Okay. But the new form does not change the essential of the program, but it makes it look nicer. We can write the gauge theory. We can write the gravity as a Saint-Simon theory. I just call it the CS theory. The important thing here is that in dimensional higher than 3, it is impossible. It is impossible to write the Einstein gravity as a gauge field theory. Therefore, you cannot expect to study 4-dimensional gravity using the same method. Okay, this is something we need to note. Another thing is to note is that in the CS description, yes, the CS description, we require the verbing to be invertible. Notice that the verbing is just a 3 times 3 matrix. This is because the verbing is used to construct a metric. Maybe we can see some derivation. I mean, we use some mathematical formalism. Okay, it's not here. Just in my note here. Okay, that's here. The verbing, it is just a 3 times 3 matrix. Okay, it's used to construct the metric. And from my understanding, when performing the plus integral for gravity, not all possible geometry configuration are included. We may need to fix the sign of G mu nu to be Lorentz or Euclidean. Anyway, you need not to sum over any possible G mu nu configuration. However, when you write it as a CS theory, even at the classical level, there are solutions that do not have a geometric counterpart. Maybe you have a solution that's equal to 0, omega equal to 0. It's nothing, and a equal to 0. There's no geometric counterpart for it. This configuration should be also considered in the gauge field theory in order to obtain a non-perturbative quantum gravity. And even Steinberg emphasized that the need to take seriously the non-invertible vibranium. Okay, the author written also states that string theory is understood as gravity on the world, and when we sum over the world, okay, we sum over the modular space of Riemann surface, it shows that the metric cannot be degenerated. So this is so you can just see that the CS theory is not exactly equal to the 3D gravity. I think this is the case. And another thing is that we know that gravity possesses diffeomorphism invariance, which is a form of parameterization symmetry. You may wonder if this is affected as gauge symmetry in Saint-Simons theory. In reality, gauge symmetry only corresponds to those parameterization that can be. Let me see. What is here? Let me see. It should appear in what? Here. Okay. The gauge symmetry only corresponds to those parameterization that can be connected to the identity. However, we will be using other diffeomorphism symmetry, which is not included in the CS description, are also important in gravity. So, what can we do? Then we can say that perhaps we can manually require the CS action to be invariant under the disconnected diffeomorphisms wheel. But I don't know, I don't sure how to do that. The witness discussion here is very insightful, but in any case, CS is not equivalent to the previous description of gravity. Okay. Then there is another aspect to consider. Gravity naturally requires to sum over different geometries, but in CS theory, it seems that to enforce this requirement, sorry, let me see. In CS theory, it seems that there's no need to sum over all geometry. You can just fix. You just can fix the manifold for the CS theory. Okay. For my understanding, in the context of gravity, when we sum over G mu nu, we are essentially sum over the geometry. However, when we write it as CS theory, we just do a partial integral for the gauge field. So we can think that A is even on a fixed manifold. So we are only sum over gauge fields. So we can provide a classification that in the CS formalism, the sum should be take over manifolds as we. Yes. If we look at it from the perspective of CS theory, indeed we can work on a fixed manifold. If you want to quantize it, you can construct a Hilbert space, but when it comes to quantum gravity, the topology can change. So it seems unlikely that you can construct a simple Hilbert space. Yes. And so is the idea of gauge gravity duality really correct? Are they truly equivalent at a non-perturbative level? Shortly after the purpose of the its duality, BTZ, the three guys, discovered a black hole solution in three-dimensional gravity with a non-negative cosmological constant. Okay, this is quite non-trivial. Even though we use it to see that the three-dimensional gravity is trivial, but it turns out there is a black hole. Okay, which is amazing. And subsequent work indicated that the black hole should be treated seriously in the context of ADS-CFT correspondence. Okay. Then it was found that the event horizon of the BTZ black hole has a positive length, which results a large entropy. Okay, it has a large entropy. Since the energy of the black hole is fixed, so there must be a large number of degenerate microstates correspond to it. It appears changing. It appears challenging to understand this within the framework of CS theory, because a topological theory does not have many degrees of freedom if you want to understand the large entropy from Chen-Simon's theory. However, some attempts have been made. Okay. The existence of BTZ black hole is a positive development. If we can quantize gravity with a black hole solution, it would be benefited for ultimately quantize four-dimensional gravity. However, in four dimensions, we encounter gravitational waves that are non-linear. So, as we can see that we cannot obtain an exact quantum solution for quantum gravity. However, an exact solution refers to at least, okay, here, an exact solution refers to at least providing the Hamiltonian near the black hole horizon and other thing. Witness discuss on this topic is truly enlightening. The most non-trivial aspect, I think, of the four-dimensional gravity is that it's nonlinear gravitational waves. For two-dimensional gravity with black hole can have an exact quantum description, but what use does it have for our goal of quantize four-dimensional? Anyway, we are now turning to the problem of solving pure three-dimensional gravity. When aiming to solve this problem of pure quantum gravity in three-dimensional, we may ask a question: what does it mean to solve it? First, we can here in this paper, we only consider the case where the cosmological constant lambda is negative. This is the only case where we know how to solve the theory. In quantum gravity, in any dimension, when a lambda is larger than 0, there are no non-perturbative solutions. One reason for this is that it seems impossible to define exact observables in the case of positive lambda. Okay, is that case? Then we just have to write the Einstein-Hilbert action Chen-Simons theory. But when we read the paper, we need to pay attention to the following points. The first one is in equation 1.3. Where is it? Here. In 1.3, the trees. Units they're starting the trees. So the trees definition involves the whole star. Okay, and since we are studying 2 plus 1 dimensional gravity, the omega represents the SO21 gauge field. It is a 3 times 3 1 form matrix. Okay, here it is a 3 times 3 1 form matrix. On the other hand, the E with an upper index represents a vector component of 3 1 forms. So it's important to note that you need to keep in mind that both omega and E are pure 1 form. It's just 1 form, not the type of Lie algebra value 1 forms in the contents. Then we use the composite field A. That is A. Okay. It represents the SO22 gauge field. Because it can be expanded using the Lie algebra of SO22, because A is a 4 times 4 matrix. Okay. Now here, now there is a question regarding the relationship between K and L in 1.3. Let's see. Here, we want to know what's the connection between K and L in the Einstein-Hilbert action. And something remarkable is that we can we can introduce topological terms into the action, such as in equation 2.1. Let me see, 2.1 or 2.2. It is crucial to note that this formula is distinct with 1.3 because this is trace, not trace star. Okay. Whether we add 2.1 or 2.2 is not significant, but we prefer add 2.2 because it is SO22. Okay. Then it is worth noting that the SO22 group can be decomposed into the product of 2 SO21 groups. Okay, this is interesting. Thus, after a suitable linear combination, we can obtain this formula. Okay, this is a suitable linear combination of omega and E. We will obtain this formula. Ultimately, we want to compare the equation here along with the Einstein gravity to include a topological term. Next, we need to review the process of quantized Selm's theory. Starting with the case where the gauge group is quite simple, it is just U1, okay, which has one generator. The gauge field A becomes a complex number because the generator is just one generator. Okay, so at each point on the manifold, a UN charge. Let me see. A UN charge is associated with it. It can be viewed as a section of a complex non-bundle L. Okay, like here. we assume that the theory is defined on a three-dimensional manifold W. If L is trivial, then everything is straightforward. You can just use this method as action, use this formula as action. However, in general, L is non-trivial, and you will find that A has a direct string singularity. This leads to a long straight definition of the action I. Okay, so we can consider W as the boundary and glue it to a four-dimensional manifold M, like this. Such as the action can be written as the equation this is. It is 2.4. However, we expect this action to be independent of the choice of M. Since M is orientable, we recall that any difference between two different choices of M is a multiply of 2 pi. Okay, leading to the quantize of k as an integer. Okay, it is because C1 is the first in class, so it must be an integer. Okay. Furthermore, we notice that SO21 what is S1 is contractible can contract to O2, and O2 is isomorphic to V1. The quantities of the SO1 gauge field will also yield K as an integer. Sometimes we may choose the gauge group to be a carving group of S1. So you may wonder why we do this. This is because U1 group is not simply connected, and it has a non-trivial fundamental group. Okay, therefore we can choose the gauge group to be a cover of U1, which is generally simply connected. The choice of an unfold carving group will lead to a different quantization of K. Okay. In the case as SO21 times SO21, you can choose the diagonal cover. Then you will obtain what? You will obtain some beautiful condition here. And it is important to note that even in the universal cover, for the universal cover, we take n equal to infinity. So this constraint doesn't work, but we still have that is the difference between k and k are to be integer. This is something always holds. Okay. So in summary, the target of this paper is to rewrite the gravity using two CS terms as described in the equation 2. The equation in the paper. It can be observed that the first term, okay, you can see that the first term, you can rewrite it like this one. The first term of this equation corresponds to the Einstein-Hilbert gravity, while the second term is the topological term we added. One remarkable property in 3 dimensions is that a vector can be expressed as an antisymmetric matrix. So just let me see, like this. So we may let me see. So we have this formula. Then the Born and Alex discovered that the central charge C equals 12 4 times K. It is an important holographic factor. Yes, this here. The holomorphic factorization can give us some hints to quantize the number k and kr. The paper, the chapter in this paper is just used to argue that this formula is right, okay, and we must choose this constraint. Note that the number 12, 24 is crucial, and we require the central charge of the left and right system to be multiples of 24. This is the demand by the holomorphic factorization. This is the only requirement. So, from let me see. From this equation, that just means that it just means that the difference between ki and kr that is equal to k prime. It should be a integer. This is the meaning. So from the requirement of holomorphic factorization, we cannot consider the Carvel group of SO21 times SO21 as the gauge group. We need to explain why. But we need to explain why SO1 times SO1 is a correct gauge group. This is because the SO21 acts faithfully on the holomorphic CFT. So other covers are not valid. Anyway, those will discuss this topic further. The core idea of this paper is to describe the pure gravity with a specific cosmological constant using CS series with central charges as multiplies of 24. However, it's important to emphasize that the three-dimensional gravity is not non-perturbatively equal to CS theory. We merely attempt to guess what values the cosmological constant should take. In the constant of gauge theory, it has to consider some non-geometric configuration. Furthermore, for the holomorphic factorization, we must consider non-geometric configuration. Okay. Then we can return to the paper. Then something make me puzzled is that the we consider the quantization of CS theory from the perspective of a different geometry, and it appears similar to the previous analysis where we push 3-dimensional manifold to a 4-dimensional manifold and calculate the difference. However, the other analysis involve taking the not this here. Here, the other analysis here involve taking the tangent bundle TW and attaching a simple line bond to it, leading to the results in this equation. But it's quite non-trivial, okay? And if for W is a spin manifold, we have this equation. Here I don't know what the meaning of a spin manifold. Anyway, I think maybe it's not so important. Okay. Now we discuss the Hilbert space of gauge fields. Well, if we can fix the manifold and denote it as C. Okay, here's a C. Okay, the C is a two-dimensional time slice, or if it is a time slice, then everything works fine. We can obtain wave function effectively construct a Hilbert space, but if C is a closed manifold, we know that the partial integral with a time slice can be regarded as a wave function. So you can think that the wave function is just a state, a vector in the Hilbert space, then you can construct this Hilbert space. But now, if C is a closed manifold, our idea is how to do it. So we can do the same thing. Our idea is to construct the Hart-Hawking wave function and say Hart-Hawking wave function just to let C to be the boundary, and you can construct any C is two-dimensional. I construct a three-dimensional manifold M in it, and you sum all only do pass integral. Okay, you need to give a representation. So you need to give an explanation for the Hart-Hawking wave function. But it is when C is a closed manifold, the meaning is non-clear. Okay. Okay, you may want to show that the wave function calculated by the partial integral with the C as a boundary satisfies the Veranda-DeWitt equation, and you can also try to map this wave function to a state in Simon's theory. However, the issue is that the Riemann surface can have complex shapes. Yes. It can be immersed rather than embedded. So generally, the Hart-Hawking wave function will not satisfy our design conditions. But the fortunate thing is that when we have a lective cosmological constant, we can resolve this issue. That is, we just reveal C as a conformal boundary at infinity, then everything can be better. Okay, this is for the discussion for me. Okay, that's great. That's the end.